This program has been compiled to explain the fault diagnosis and maintenance procedures that can be carried out on a ZF Ecomat gearbox. This unit is currently fitted to the Leyland Olympian, Lynx and Tiger vehicle ranges. The specification of the gearbox varies depending on the application. For example, the Leyland Lynx has a 4-speed gearbox, the Tiger a 5-speed, and the Olympian a 4 or 5-speed unit with an angle drive. During this program, we will be conducting our test procedures on a 5-speed gearbox fitted to an Olympian. The fault procedures will apply in the main to all gearbox specifications. However, where differences in component location do occur, this will be covered. From a safety point of view, never conduct any of the static running tests in a confined area. Ensure adequate ventilation for the exhaust. Chock the road wheels and apply the park brake. When working on the gearbox, display a suitable warning notice in the driving compartment. Turn off the battery isolation switch when applicable. During running tests, exercise extreme care when working near to rotating shafts, drive belts and ventilation fans. Before proceeding with the fault diagnosis, let us briefly look at the main component layout in the gearbox, basic operating principles and unit location. Contained in the gearbox is a compound epicyclic gear train and a series of hydraulically operated clutches which lock the various members of the gear train to engage the gears. These clutches are identified by a letter A, B, C, D, E and F. When any of the gears are engaged, 2 clutches are always in operation. When first gear is engaged, clutches A and F. Second gear, A and E. Third, A and D. Fourth, A and B. Fifth, B and D. C and F for reverse. The drive from the engine enters the gearbox via a torque converter which has a lock-up clutch. Located here is a hydraulic retarder unit which supplements the main vehicle braking system. An oil pump within the gearbox supplies oil pressure to actuate the gear clutches and provide lubrication for the gearbox main running components. The main external control for the unit is the control panel. A load sender is connected into the throttle linkage on the engine to relate throttle position to the control system. 2 speed sensors are fitted, one on the output shaft to monitor road speed, and the second recording gearbox input turbine speed. Finally, the driver selector switch. This can take a number of different forms. On the Tiger, a 6-button unit. The Lynx, 3 or 5 button, and the Olympian, a 5-button. With N selected, the gearbox is in neutral. R, select reverse. And D selects the starting gear and places the control in the automatic range. Where hold buttons are available, the following functions apply. With button 1 selected, the vehicle will not change up from the starting gear. With button 2 selected, 4th gear will be held on a 5-speed gearbox, and 3rd gear on a 4-speed unit. However, in both cases, the gearbox will change down to the starting gear if road speed is reduced sufficiently. With the remaining unit, this is only normally used on 5-speed gearboxes. Button 1 will hold 1st gear, 2 2nd gear, and 3 will hold 4th. When D is initially selected, providing the gearbox turbine is not indicating engine revs in excess of 900 RPM, and the load center is not indicating throttle, the control panel signals electrically a solenoid within the gearbox, which in turn triggers the hydraulic control to engage the A clutch. To complete the first gear engagement, the F clutch is energized in the same manner. As the vehicle accelerates, the torque converter is in operation until the turbine sensor indicates an input speed of 900 to 1000 RPM. At this point, the control system operates the lock-up clutch solenoid and hydraulics, and the converter clutch engages to lock the converter to eliminate slip. During this period of acceleration, the output sensor indicates road speed to the control system, and at a predetermined speed, the F clutch is released and E engages. With the A and E clutches engaged, second gear ratio is in operation. As speed increases further, the third gear engages, A and D clutches. Fourth, A and B, and finally, B and D for fifth. Should road speed be reduced progressively, the gearbox will downshift back to the starting gear. The oil pressure available in the gearbox varies between 8 to 18 bar, depending on engine revs and gearbox loadings. For example, with the engine at idle, the pressure will be 8 to 10 bar. With D selected, as the engine revs move up to a fast idle, the pressure increases to 18 bar. This level of pressure remains until the gearbox has changed up into second gear. At this point, the torque converter is locked up, and because of the reduced input torque to the gearbox, the main pressure is reduced to 10 bar for all the remaining gears. It should be noted that the 18 bar oil pressure is only available when the torque converter is in an unlocked condition to eliminate gear clutch slip due to the extra torque multiplication. During clutch engagement, there is a very short period of controlled clutch slip to ensure smooth engagement. This is accomplished by regulating the initial pressure buildup in the clutches. During normal operation, the gearbox is subjected to varying power inputs, which means that the rate of pressure rise has to be adjusted during engagement to maintain smooth gear shifts with minimum slip. This pressure control is known as throttle pressure modulation. The load sender indicates to the control panel the throttle position which relates to the engine power input to the gearbox. The control panel at gear changes triggers a hydraulic valve in the gearbox for a 1.5 second period to trim the engagement pressure to suit the transmission load. It should be appreciated that if the load sender does not send correct information to the control panel, it can cause slip in one extreme or harsh engagement in the other. Further details of the correct adjustment procedures and the gearbox hydraulics will be covered later in the program. During this program, we will be looking at fault diagnosis procedures at 2 levels. 1, using only basic equipment, namely a test lamp, multimeter, pressure gauges, and finally, the special test equipment required for more in-depth diagnosis. In order to follow the various test procedures, we would recommend that you have to hand the program's support notes and fault charts for reference. The first fault area we shall be looking at is a no-drive condition in D and R. First, check whether the engine revs freely or not. If it labors, like this, and the engine only achieves approximately half revs, this is known as a stall condition. If this situation exists, check that the vehicle brakes have been released. If they have, the next procedure is to pass the ignition and gear selector through a start sequence. Switch off the ignition, select N. Restart the engine and select D. If drive is now available, this indicates that the control panel has been in a lock-up condition in a high gear. This situation can arise if there is a sudden loss or deterioration of the speed signal from the output sensor. This can be due to a fault in the output sensor or wiring, or if the road wheels have been suddenly locked under heavy braking. If the stall no drive still exists, disconnect the main electrical supply plug at the gearbox. and if the problem persists, this indicates seizure of the gearbox clutch or running train component. Had the engine revved freely when the plug had been removed, this would point to a failure either in the control panel or driver selector switch. So therefore, to check the selector switch operation, first remove the cover plate in the driver's compartment and disconnect the plug. If the engine now revs freely, the selector switch is at fault. But if the problem persists, the control panel is at fault. If we now revert to the first fault check in this sequence and the engine had revved freely, our initial check would be the prop shaft. If the prop shaft was found to be rotating, this would indicate a final drive failure. Alternatively, if the shaft is not rotating, a check should be made on the gearbox oil level. On the dipstick, there are a number of level marks to take account of various gearbox oil temperature ranges. Details of these will be dealt with later in the maintenance section of this program. However, for the purposes of this exercise, let us assume that the oil temperature is between 80 and 90 degrees centigrade, which is the normal operating temperature. With the engine at idle and N selected, the oil level should be between these two marks. It should be noted that the oil level would have to be extremely low to cause a no-drive condition. If it is necessary to add a lot of oil, a check should be made for oil leaks. If there are no visible signs of oil leaks, the low oil condition may be due to incorrect initial filling procedures. On the assumption the oil level had been correct, you should check the idling speed of the engine. If it is in excess of 900 RPM, the control system will inhibit any gear selection. Our next check is the load sender. Again, in this instance, if incorrectly adjusted, and it is indicating a part throttle condition to the control system, gear selection is inhibited. When set correctly, with the throttle at idle, the lever should align with this throttle mark, and here for full throttle. The stroke between idle and full throttle can be adjusted by moving the ball joint within the elongated hole in the sender lever, and the stroke position by adjusting the rod length. If adjustment is correct, check the main oil pressure at this test point on the gearbox. Remember to select the pressure gauge with a range in excess of 18 bar. With the gauge installed, start the engine. A pressure of 18 bar at a fast idle should... If there is no reading or a low reading, remove and check the condition of the gearbox oil filter, which is located in the gearbox sump. Before removing the filter, it'll be necessary to drain the gearbox oil. The filter is retained by this cover plate. After removal, the filter element can be withdrawn for inspection. Further details of this filter procedure will be given in the maintenance section of this program. Providing the gearbox filter and oil maintenance has been carried out at the correct intervals, if filter blockage occurs during the interim period, the cause of the debris buildup must be investigated, as this gives an early warning of gearbox component failure, such as clutches and running train components. If the oil pressure had been correct, a check should now be carried out on the load sender to check its supply voltage and variable resistance. First, disconnect the plug close to the unit and connect a voltmeter between terminals 2 and 4 on the cable plug. Details of the plug numbering are in the program notes. The reading should be 9 volts. If the voltage is higher, this will result in the load sender signaling to the control panel a high throttle condition and will inhibit gear selection. If this is the case, the panel is at fault. If correct, carry out a variable resistance check on the load sender plug on connections 2 and 4. You will find that in the idle position, the resistance reading will be 700 to 1000 ohms, and when the arm is moved to full throttle, the reading will drop by approximately 300 to 400 ohms. Providing you get these readings, this is a general indication that the load center is correct. On this example, the reading varies between 800 ohms to 500. If there is no variation with lever movement or resistance readings are substantially outside the figures quoted, the unit is faulty. If this is in order, our next check is on the gearbox harness plug to check the supply from the panel using a test lamp. Always reference the location lug in order to identify the correct pin or socket. The solenoids controlling first gear are A and F. Therefore, to check the supply, select D and connect a test lamp between sockets A and N. N being the common negative for all the gear solenoids. If correct, connect between F and N. If in order, the bulb should light in both cases. To check reverse, select R and connect the test lamp between C and N, and F and N, and again, if in order, the bulb should light in both instances. Assuming the results are correct, carry out a resistance check on the gearbox solenoids using a multimeter. Again, for information, the program notes have details of the gearbox socket identification. By checking across connections A and F and N pins on the gearbox for first gear, and C and N, and F and N for reverse, the correct reading should be between 64 and 71 ohms. It should be noted that the readings will vary depending on the solenoid temperatures. At the low end of the scale, when they're cold, and high when hot. If the reading is substantially outside these limits, or there is no reading, there is a fault within the solenoid or gearbox wiring. If all the readings are correct, this indicates a possible hydraulic fault in the gearbox. To assist testing in this area, a special cable and plug is available. The cable ends are marked for each of the gear solenoids, and also for the output and turbine sensors. LM for the speed sensors, and N for the gear solenoids. This test lead provides a very convenient means to check the electrical resistance of the solenoids, and also provides a safe means of energizing each individual solenoid with 24 volts if required. If the solenoids are energized by this means, they produce an audible click, which confirms operation and that they're not jammed. It should be noted that the test leads for the two-speed sensors, which are green, must not at any time be fed 24 volts. Otherwise, serious damage will result to the sensors. If we move back to the cable plug and no supply was available in any one of the connections A, F and C, it would be necessary to carry out a continuity check on the cable from the gearbox plug to the control panel. To do this, remove the panel plug by releasing this clip and hinging the plug out carefully. Always ensure when carrying out this exercise that the ignition is switched off. The plug pins are numbered in the following manner. Details for reference are available in the support notes. Because the F clutch is common to both first and reverse, and also the negative, it is only necessary to check from F on the gearbox plug to pin 5 on the panel plug, and N to 24 for the negative. If there is no reading in any one case, there is a cable fault. If there is a reading, before changing the control panel, check that the gear selector switch is giving the correct input signal to the panel. To do this, again disconnect the panel plug and carry out a continuity check between pins 31 and 24 with D selected and the ignition switched off. To check R, connect between 28 and 24. If the reading is correct, there is a panel fault. Should there be no reading, it'll be necessary to carry out a further continuity test on the wiring from the panel plug to the selector plug. The plug sockets are numbered in the following manner, 1 to 8. The D check is from pin 31 on the panel plug to socket 3, R, between 28 and 7. And finally, the negative, 24 to 6. If there is continuity on all the cables, the selector switch is faulty. Because reverse gear is operative, we can discount a number of areas, such as the main gearbox oil pressure, oil level, rear axle, load sender, and concentrate just on a first gear fault. Initially, establish whether there is a supply from the control panel to the gearbox. Connect the test lamp across the cable sockets A and N and F and N, which are the solenoid supplies for first gear engagement. If the bulb does not light, carry out a continuity test from the gearbox plug to the panel plug. A to 18 and F to 5. If correct, check the D input from the gear selector switch across connections 31 to 24, with D selected and the ignition switched off. No reading indicates a selector switch or cable fault. So therefore, carry out a continuity test on the selector plug on sockets 3 and 6 to eliminate the switch from the cable. Moving back to our original check on the gearbox plug, if the test lamp had indicated a power supply, you should carry out a resistance check on the A and F solenoids. Checking across the A and N and F and N pins on the gearbox socket. No reading or a high reading in any one case indicates a solenoid or internal wiring fault. If in order, operate the selector switch from N to D a number of times. And in most instances, the solenoids within the gearbox will be heard to click. Confirming that they're not jammed. If in order, there is a clutch or hydraulic fault within the gearbox. Further details of the hydraulic control will be given in the next stage of this program. To assist with our understanding of the hydraulic circuit, let us look at the theory of the system. Oil is drawn from the gearbox sump through a filter by the oil pump to the main pressure relief valve, which maintains a system pressure of 10 to 18 bar, depending on the gearbox operating mode. Oil passes to all the gearbox solenoid and hydraulic valves. And when D is selected, first gear is applied, and the A and F clutches are operated. As the vehicle's speed increases, the F clutch releases, and the E clutch engages, and second gear is operative. This continues through to fifth gear. As previously explained, the clutches during a gear shift have pressure modulation to control the clutch engagement to take account of varying engine loads. Oil from the main supply passes to the throttle modulator valve, and when the gear selector is in N, the modulator supplies oil to all the gear solenoids at 6 bar. However, when D is selected and the first gear clutches start to engage, the control system electrically pulses the modulator for approximately 1.5 seconds which drops the modulator pressure down to half a bar. With low modulator pressure, the clutch operating pressure rises slowly to cushion the clutch engagement. When a gear shift takes place at full engine load, the modulator pressure remains at 6 bar. The result is that the rate of pressure rise in the clutches is increased to offset any possible clutch slip. The modulator pressure will vary depending on the throttle position between half a bar and 6 bar during gear shifts. The strength of the electrical pulse from the control panel dictates the modulator pressure. For example, a strong pulse gives low modulator pressure and a weak pulse, high pressure. The panel, during these various throttle conditions, receives its information from the load sender. From the lock-up clutch hydraulics, there is a sensing line to the main pressure relief valve. When the lock-up clutch is in operation, oil pressure acting on the main pressure valve sets its operating pressure to 10 bar or 18 bar when the clutch is disengaged and the torque converter is in operation. Looking now at the remaining circuit, oil passes to the torque converter where a safety valve set at 8.5 bar is installed to protect the converter in the event of a high pressure buildup. A counter converter pressure valve is installed in this line to ensure that the converter pressure is maintained during normal running to 4 bar. From this line, pressure is signaled to the hydraulic control for the lock-up clutch. This enables the speed of the lock-up clutch engagement to be adjusted depending on engine speed and load, thus ensuring smooth engagement and minimum slip. To continue, the oil passes to a cooler changeover valve. Through an oil cooler and back through the changeover valve before passing on to lubricate the gearbox. The lubrication pressure relief valve is fitted to control maximum pressure. It should be noted that the cooler changeover valve is held in this position by oil pressure from the main supply via the retarder control valve. A second line ensures that the retarder operating valve is held closed. When the retarder is operated, an air supply is introduced which moves this control valve to dump the oil pressure from the cooler changeover valve and the retarder valve. The changeover valve now moves to a new position. Finally, the retarder valve now allows oil to the cooler changeover valve, which has moved to a new position and directs oil to the retarder. The returning oil from the retarder passes back through the changeover valve and through the cooler. It should be noted that during retarder operation, the oil from the converter output through to the lubricating oil is not cooled, thus giving priority to the retarder. Retarder operating pressure is proportional to the original air signal on this valve. For example, with an air pressure of 1.2 bar, the retarder oil pressure is approximately 2 bar, and a 3 bar input gives 4 bar. From the retarder system, a sensing line signals this pressure rise to the retarder valve, and this closes the main supply when it overcomes the air pressure signal. To complete in this area, a sensing line is connected from the retarder output to the throttle modulator valve. This pressure signal enables the modulator valve to increase the rate of pressure rise in the gear clutches during a downshift to offset the increased gearbox torque when the retarder is in operation. Although in this diagram the hydraulic control is shown as one unit, it actually consists of a solenoid valve, pressure control valve, and a cutout valve. If the gear is not engaged, the solenoid valve is closed. The oil pressure supply from the main gearbox system only travels to this point. However, it can pass to the hydraulic control piston, which is again closed. The oil is allowed into this section of the control piston and the remaining area via the cutout valve. Because of the pressure difference across this piston, it holds the main piston closed. During this condition, oil pressure from the pressure modulator valve is present in this chamber at a pressure of 6 bar. When the gear is selected, the solenoid valve lifts off its seat, allowing oil to pass to this side of the piston, and also to the cutout valve. The cutout valve moves against a spring, which allows oil from this small section of the main valve to exhaust. Because there is now a pressure difference across this piston, it moves to the right, allowing the modulator pressure to push the main valve to the open position. Oil then flows round the spool valve and through a drilling into this chamber. At the same time, oil flows to the gear clutch piston and also through to this piston via a restrictor. A check valve in this drilling is held onto its seat and does not come into operation until the gear is released. As pressure builds up, the oil pressure acting on this piston cancels out the initial opening effort of the modulator pressure. However, the valve is held in the open position because pressure has now built up behind this piston. The throttle modulator pressure at the point of gear engagement can vary between 6 down to half a bar. This variation enables the initial speed of valve opening to be controlled, and hence the rate of pressure rise in the clutches to give a smooth engagement to match various transmission loadings. Now let us continue with a further series of fault conditions. With this fault, you should first of all establish whether the gearbox is attempting to change up from first to second or remaining in the starting gear. For example, if the gearbox selects neutral at the point of gear change, you would concentrate on a second gear fault path. Alternatively, if it remains in the starting gear, you would follow a fault path to check the speed signal from the output sensor to the control panel. Let's assume that neutral is selected at the point of gear change. You should carry out a resistance check on the E solenoid. E to N, followed by a cable check from the gearbox to the panel. E on the harness plug and pin 8 on the panel plug. Should these checks be in order, this indicates a fault either in the gearbox E-clutch hydraulics or control panel. In order to check that the output sensor is sending a speed signal to the panel, connect a test lamp from this plug, known as BN2, located in the front junction box. Connect from wire 20 to a positive supply. If the vehicle is now driven at a speed just above 3 miles an hour, the light should come on at this speed, provided, of course, the speed signal is correct. This connection is used on some bus applications to inhibit door operation above 3 miles an hour. If the light does not come on, check the resistance of the output sensor on socket V and M on the gearbox. The resistance should be approximately 1080 ohms. Should there be no reading, a fault exists in the sensor or in the gearbox internal wiring. If the reading is correct, check the sensor resistance at the panel plug on pins 6 and 7 to establish whether the cable from the gearbox to the control panel is serviceable. In order to carry out further checks to decide whether the fault is in the gearbox or the control panel, it will be necessary to use the special test equipment, which can monitor all the input and output signals to the control panel. To install the test equipment, first remove the panel plug and install the test plug and cable. finally, replace the panel plug. To check the system, you can either drive the vehicle or operate it statically. In this particular instance, we will be carrying out a check with the vehicle in motion. With the ignition switch on, first set this control to the drive position, and this to AB, as this will enable the frequency from the output sensor to be monitored on the lower meter. You will find also that the meter at the top will show a reading of half a volt with the throttle at idle and 4 volts at full throttle. This meter monitors the variable voltage output from the load sender on the engine. If these readings are outside these limits, adjustment must be made to the load sender as specified earlier in this program. To commence the test, start the engine and select D. You should find that the A and F lights will come on, indicating that first gear has been selected by the panel. Next, drive the vehicle, and if the speed sensor is functioning, there should be a frequency reading on this meter. At a predetermined speed of approximately 1000 Hertz, the panel, if functioning, should select second gear, and this will be indicated when the F light goes out and E comes on. If the panel does not change up, make sure that the frequency reading is correct. Should it be low or no reading, in view of the checks carried out earlier, the air gap between the sensor and the tooth wheel in the gearbox may be too wide. If the panel responds correctly, there is a problem in the gearbox, and if not, the panel must be replaced. If it is necessary to replace the sensor or check the air gap, you should proceed as follows. The output sensor is located at the rear of the gearbox under this cover. Disconnect the wire. Unscrew the sensor, but take care not to drop the shims into the casing. To establish the correct shim thickness, it's necessary to measure the distance from the casing to the tooth wheel. This can be achieved by using a simple bar with a circlip attached. Move the circlip to within 1/4 inch of the end of the bar. Push the bar in until contact is made with the tooth wheel, but make sure it is on the top of the tooth. Measure the distance from the end of the bar to the circlip and record the measurement. This measurement must be repeated at 3 equal intervals in case there is runout on the tooth wheel. Record the average of the 3 readings. If the length of the measuring bar is deducted from the length of the sensor and a figure of 0.6 to 0.8 millimeters is added, this will give the required shim thickness for the correct running clearance of 0.6 to 0.8 millimeters. Let's now look at the static tests that could have been carried out using the test equipment as an alternative to the running test. To do this, the test equipment controls must be set in the following manner. Move this switch to the test position. Set this control to LL. This control represents the driver's selector switch and should be set to D. The remaining control should be set to AB, which enables the output speed frequency to be read from this lower meter when this ABTR control on the side is rotated clockwise. To commence this test, turn the vehicle ignition on and select D on the driver's control. The A and F lights should come on. Next, rotate the ABTR control clockwise to increase the vehicle speed. The control panel should up-change to second gear, and the A and E lights should come on. You will notice as the ABTR control is moved that the frequency is shown on the lower meter. If the panel shows the correct lights, the problem is in the gearbox. If not, the panel must be replaced. For guidance, if a gearbox fault is identified, the most likely area is either the solenoid or hydraulic control valve, as opposed to a clutch or piston problem, because the latter two items normally fail progressively, and partial slip will be evident before reaching a complete lack of drive.